All right. Good morning, afternoon, or evening, everybody. Welcome to the Discover and Access NESA's Near Real-Time Global Flood Products ESDIS Data Training webinar. This is your host, Jennifer Brennan. It is 2 p.m. Eastern Daylight Saving Time, so let's get started with just a few logistics. To ensure the best audio experience, all participants have been placed in silent mode. But if you have any issues or you have any questions, what I'd like for you to do is enter those into the Q&A panel rather than the chat. And you should see that on the right side of your screen. There should be actually a question mark icon that you should see in the bottom right. It might look like it's kind of like a floating icon. Click on that to activate your Q&A, or you might be able to click on the three dots in the bottom right corner to pull up your panel options and insert a check mark next to the Q&A panel. All right. Today's webinar is being recorded. The recording will be posted online to YouTube within a week of completion. And then what I'll do, once completed, I'll send an email to all registrants and participants that includes links to both the recording and also the presentation slide deck used within today's webinar. As far as timing is concerned, today's event will be 1 hour and 15 minutes long, with an hour being allocated to the presentation and live demonstrations, and a 15-minute question and answer period to begin after the presentation. Depending on the volume of questions we receive, we may extend the Q&A session, but we will have a hard cutoff of 3:15 p.m. Eastern. During today's webinar, we will have one speaker and two additional Q&A panelists from the NASA LANCE team, Diane Davies and Jenny Hewson. Our speaker for this afternoon is Dr. Dan Slayback. Dan is a research scientist within the Biospheric Sciences Lab at NASA Goddard Space Flight Center. And actually, let me move this slide forward a little bit. He's going to kick us off today with a brief history of the product, an introduction to NASA's Land Atmosphere Near Real-Time Capability for Earth Observation, or LANCE. From there, he will discuss the approach and methodology for creating the global flood product, present recent updates, and discuss the validation and evaluation of the product. Next, we will transition to a discussion of product caveats and limitations that users need to be aware of. After this, Dan will provide both an overview and live demonstration for several data discovery and data access tools, which will include the data download via LANCE, the beta version of the new flood viewer or dashboard, and APIs and NASA Worldview for imagery mapping and visualization. And then finally, we'll touch upon the product archive for historical analysis and wrap up the webinar content with some information about future direction. After Dan is finished with his presentation, I'll open up the final optional polling questions, and then we'll transition directly to the question and answer period. Before I toss it over to Dan, I wanted to cover just a quick note about the Q&A session. We're going to try to address all of the questions within the time allotted, but if we're not able to address your question during the Q&A period, our speaker or our Q&A panelists will be able to follow up with you offline. So with that, it is my pleasure to introduce today's speaker, Dr. Dan Slayback. Dan?
So anyway, moving along, let's jump into this. I wanted to, before I get into how the product works and all that jazz, I wanted to show you what the product is, what it looks like, so you can sort of see where we're coming from or where we're going. So I'm going to run through a few examples. Here was the product that we delivered about 12 hours after the Kakhovka Dam was breached in Ukraine 2 years ago in June. The breach happened in the middle of the night, and we fortunately got a clear Terra observation, MODIS Terra observation the next morning, and this flood product was out the door within a couple of hours of that. So this shows a couple things. For one, what we're reporting, which is flood and surface water. We detect water, and then we have a very trivial comparison to decide if it's flood or surface water. So that's the product as you see it. You can also see the pixelation. It's 250 meter data. So at this scale, you can sort of see the pixelation, especially along the river. This is not, high resolution data, but it is global and daily. So that is the one of the key advantages of this, using these data sets. Also in Kherson City, there was much more urban flooding going on that we did not capture because the product is typically does not work well in urban areas because you have a lot of dry buildings or buildings that aren't completely submerged, and cars and trees and things. So in complex landscapes where you don't have 250 meters of observable water, it may not work very well. But it's near real time and available always or everywhere if the clouds are cooperating. Here's another example. This is from major flooding in Southeast Asia back in 2011. This was quite an unusual flood event. Typically in the fall, at the end of the rainy season, the Tonle Sap Lake in the center of Cambodia there does flood, but this was much more flooding than is typical. And the flooding in central Thailand on the left was also quite above normal. So this sort of just shows the kind of broad scale flooding that we can capture with probably a single modus observation. Here was the flooding in Pakistan 3 years ago in 2022. This was the historic flooding that made lots of news on the lower Indus River, showing this in the Worldview application, which I'll talk about a little bit more later on. Here was earlier flooding in Pakistan back in 2014, a time series we did with the older product, just showing that you can, if conditions, if cloud permits, as it did at this time, you can actually watch the water flow down the river, which was quite interesting. The pulse of flood water flow down the river, which was quite interesting. More recently, earlier this year, here are some examples from our VIIRS flood product. So this is taking over from Modus, as Modus will be retired in the near future, which I'll talk about briefly ahead. But VIIRS is the replacement, and we have a replacement flood product operational now. So on the left is flooding in U.S. Midwest in April, and on the right in Argentina in May. So just a brief outline, as you saw on Jennifer's slide, product overview, which you've now seen. I'll next talk about a brief history, then the methodology and approach, updates, evaluation, limitations, distribution, archive, and where we're going in the future. So the brief history is that back in 2005, Bob Brackenridge at Dartmouth College had founded the Dartmouth Flood Observatory and was working a manual method to detect floodwater in Modus rapid response imagery, which had recently come online. This is a predecessor to the Lance effort, which I'll discuss the next slide. But the rapid response imagery was imagery that was available within, I'm not actually sure what the timeline was back then, but within a few hours, if not certainly the same day as the observation. He was mapping flood from what were JPEGs, not really intended for data analysis, but he managed to make it work. So in 2010, NASA Goddard's Office of Applied Science decided this would be a great opportunity to automate this so that it doesn't rely on people to find time and energy when a flood might be happening to manually run some mapping. So that's when this whole project initially got going, and I became involved about that time. So by 2012, we had started full global flood mapping with our, what we call now the legacy product. An example of that is on the right. This was also delivered in these graphic map products like this, covering 10 by 10 degree tiles. This, worked well, but it was on PI managed servers and resources, which is always difficult to maintain. So in 2021, we transitioned this to live fully within the MODAP's processing system here at Goddard within Lance. And that provided much more robust production. Everything runs on two separate sets of machinery. So if one is down for any reason, the other one is running. And minimize the latency to the minimal possible. As soon as that data comes through, the flood product is spit out. So that started in 2021. Earlier this year, we launched the VIIRS product, as I mentioned earlier, the sort of replacement for Modus. And just to mention what Lance is, we say Lance, this is the Lance flood product. You'll hear Lance a lot. LAND-START stands for Land Atmosphere Near Real-Time Capability for Earth Observation. This is the sort of virtual system that leverages existing compute resources to generate products from all the sensors you see in the box within a few hours of observation, typically, versus a standard product might take a couple days or longer to collect all the ancillary data and get it out the door. So the purpose of LANC-supported products is for near real-time applications where people want to see what's going on right now or as soon as possible. So the approach, there's 4 basic steps. It's not really too complicated overall. We detect water. That's fairly simple. Then we use what we call multi-look compositing to deal with multiple water detections. And that's sort of a key part of our recipe. Then we do some terrain false positive masking to get rid of some problematic false positives. And then we identify flood, which is a simple comparison to a reference water layer, and that spits out the flood product at the end of that chain. So I'll talk about each of these in some more detail next. So the water detection operates on, so there's, as I mentioned, there's the MODIS product, which is what's been around for 15 years, and then the VIIRS product. So the MODIS product source imagery is from the Moderate Resolution Imaging Spectrometer. This is an instrument that's been on board 2 separate spacecraft, Terra and Aqua, in orbit for, since 1999 or 2002. So these birds are quite old in the tooth and well beyond their design lifetime. But, talk about NASA engineering, competence and effectiveness. They're still delivering data. Unfortunately, they're out of gas, but so their orbits are degrading. So they will be out of commission in those shorter to medium term. But they deliver 250 meter data global, each one global daily, so twice daily with both of them. It is optical data, so we're not seeing through the clouds. It's a polar orbiter, so you see the orbit on the right one goes from north to south, the other from south to north, and you stack up those tracks over the course of a day, and you get full global coverage, which you see in the bottom. You will notice gaps near the equator. Those are equatorial swath gaps. Those move with every set of orbits, so you don't have missing data every day in the same place. It shifts around, so it's not too much of a problem. So that's MODIS, the source data for the MODIS product. VIIRS is very similar. It is on board 2 NOAA satellites, NOAA 20 and 21. It's also on a third, but we're only using the data from NOAA 20 and 21, which have been up for a number of years. The main differences from MODIS are the 375 meter resolution, so it's going a little coarser. Also, both satellites observed in the afternoon with only about a 40-minute separation in time, 1:30 to 2:20 p.m., roughly local time. MODIS was separated by about 3 hours. We like multiple observations because during that time, clouds move, and so you can see what was under the cloud before if it moved along. And it also helps with our cloud shadow problems, which you'll hear much more about shortly. But even with only a 40-minute separation with VIIRS, it is still useful to use both of those observations, so we do. It also gets rid of the equatorial swath gaps, so those are gone in the VIIRS product, which is certainly nice. Okay, so the water detection algorithm is a fairly simple threshold-based algorithm. There's 3 parts, as you see there. The key part that does all the work is the one at the top, the near-infrared red ratio. This is what Bob Breckenridge had originally developed, and we've sort of kept it going more or less as is since that time. It has worked equally well on VIIRS, which have slightly different bands, but close enough for the purposes of this, as it has on MODIS. So the product is delivered in 10 by 10 degree tiles. That is not the source data. That is not MODIS or VIIRS. That is our product. So a lot of the examples show this typical 10 by 10 degree tile framework. So that's where that's coming from. So for a typical acquisition, we have an input image from, you see there, MODIS Aqua. covering Southeast Asia. Again, the same 2011 event, because it was such massive flooding, you can see it quite clearly even at this zoomed out scale. Apply the water detection algorithm, and we get a binary water map. So that's, really pretty straightforward overall. Just detect water and move along. The second step is what we call multi-look compositing, and this does a lot of the work of turning that water detection into something that's really more usable. The problem with a single water detection is you will have a lot of potentially false positives from cloud shadows, and then you obviously don't see where the cloud actually is blocking the surface. So we have 3 different composites, a 1, a 2, and a 3-day. For each composite, you just sum up all the water detections you have over that period, either over 1 day or 2 days or 3 days, and compare that sum to a threshold. The threshold is typically the number of days. So 1 for a 1 day, 2 for a 2 day, 3 for a 3 day. It does change when the swaths overlap and you have additional observations than just 1, 2, or 3, or 2, 4, or 6 per day. But that's the basic idea. And that allows you to, clouds move and you can still get a detection from the other orbit or a different day. And the cloud shadows are also moving around, so becoming less problematic. The next step is the terrain false positive masking. So aside from cloud shadows looking like water, terrain shadows also look like water. So we have 2 steps to deal with this. One is we apply monthly computed terrain shadow masks, as you see there on the left. So computed at both 10:30 in the morning and 1:30 in the afternoon, applied to the relevant observation. That does a lot of the work, but it does leave some residual shadow false positives. So then we apply a general topographic mask, the hand mask, and that tends to get rid of almost everything else. And there'll be more detail of that ahead. So the final step is the flood identification. This is really quite trivial. Take your detected water, compare it to a reference water map. If they align, call it surface water. If they don't align, call it flood. The reference water map is the Mod 44W product. It's a land water mask. It's totally independent of this product. And we'll talk about that a bit more ahead as well. So a little more detail on the false positive masking. As I've said, shadows look like water with the 2 bands that we have available. So these sensors have more than 2 bands, but the highest resolution are just red and near infrared. And so we want, of course, the highest resolution product. So we use those bands to develop the product. And in both cloud shadow, any shadow is very dark, as is water, and it's very difficult to discriminate. Terrain shadows are obviously in the mountains, mostly in the winter. The computed terrain shadow masks get rid of from 75 to 90% of those, but that can still leave a significant number. So the hand mask tends to get rid of the rest of it, or most of the rest of it. Cloud shadows, the multi-look compositing, that is really, one of the main reasons to do that, as well as to see under the clouds as they move. They can occur in the same place, so you will still get false positives in the 2-day product, much less so in the 3-day. It's really critical, if at all possible, if you're looking at the product manually, to look at the source imagery so you know where the clouds are, and you know either where you're not seeing flood because it's totally cloud covered and there's no point, or where you could have some confusion with false positives. So we'll show some examples of that ahead. So here's a more detailed walkthrough of the compositing and masking processes. Here's an image from Modus Aqua in the Alps in winter. Not a great time to be looking for flood, but nevertheless, it demonstrates some of the issues. So we see snow-covered mountains in cyan and this false color, and clouds in white and pink. The water detection just applied to that image returns this with all these areas in yellow. This is, quite a mess. Very little of that is actual water. We're only seeing part of Lake Geneva, not all of it. So, not really anything usable. If we composite over 2 days, so that means we're putting 4 images into it, and I'm not showing you all 4 just to not overwhelm you and make this thing go on too long. But with the 2-day composite, we get rid of a lot of the cloud shadows, not all, but you can see, many of them start to disappear. The terrain shadows get worse, so that does not help with those guys. Here's the terrain, just to give you a general idea of what we're dealing with in that image. Here's the terrain shadows we compute for 10:30 in the morning. Here's the shadows for 1:30 in the afternoon. So the sun moves, the shadows shift a bit. Here's the water detections before applying the terrain shadows. And here's after. So it does a lot of work, but there's still some residual shadows poking around the edges of the mountains. We tried quite hard to get rid of those with different terrain shadow masking, but it's apparently a complex problem that was not too tractable. So we moved to the hand mask. This stands for height above nearest drainage. So it is a measure of the vertical height between a pixel and the nearest drainage. The drainages are defined by the procedure as well. So there's 2 parameters you have to determine to implement a hand mask. And we tested these, globally to try to find the best compromise for our product. And on the vertical threshold, we chose 30 meters. So if a pixel is 30 meters above the nearest drainage, we believe it is unlikely for that pixel to retain floodwater for any significant period of time such that it might be observed. So this is the resulting mask. If you apply that to the mess that you saw earlier, you get rid of, almost everything. The remaining yellow is, most of those are lakes. There might be a few cloud shadow false positives, and certainly you could pick those out if you look through the imagery directly. But it does, it's much, much cleaner. So that is the all the compositing and shadow masking business. But there's more detail to show you on the compositing, the multi-look compositing. So as I mentioned, we composite over 3 periods, 1 day, 2 day, 3 day, meaning there are 3 separate products you might want to look at or might not, because it does get kind of complicated. But the 2 day is what we call the standard product. This is probably the best place to start. It's generally not too contaminated with cloud shadow false positives, but it might have a few, it might not. The 3 day will have very few false positives, but it will be less current because it is using imagery over a 3-day period. The 1 day is the most recent. It's just today's data or the product date's data. But if there are cloud shadows, not all cloud shadows are detected as water, but if there are clouds, you may well have false positives. So which one you want to use really depends upon the cloud conditions and what your tolerance is for false positives and negatives, and your need for the most up-to-date information. If it's clear, if you look at the source imagery and everything's clear, then just use the 1 day and be done with it. But it's rarely, it may well be clear in your area, but it's rarely clear in any large region, such as a 10 by 10 tile, completely. And if you're very sensitive to false positives, then maybe stick with the 3 day. But it's really best to look at the imagery and see what you're getting. So I will show you an example of that in more detail. This is for flooding that occurred in southern Poland in September of last year, just about a year ago. And if you looked at the 1 day product, and this is our flood viewer, which you'll see more of later, you'll see the flood reported in pink there, and you might think, well, this looks pretty reasonable. That sort of seems to follow rivers possibly, or, sort of linear type patterns that you might expect from flooding. And if you look at the MODIS imagery, you might think, oh, we're really doing good. There's one cloud and it's not casting problematic shadows, so this might be fine, and go with it. Then if you look at the MODIS Aqua image, you'll see where there are some problems. There are definitely cloud shadow false positives along the north side of that central cloud. Not on all the clouds. It is it doesn't happen everywhere, or always when you have cloud shadows, but it can. But there's still real flood here that we're detecting. If you look at the 2-day composite, we get rid of most, maybe all of those false positives. The amount of actual flood we're reporting also declines a little bit. So depending upon, what area you're specifically trying to look at, this might be good. If you look at the 3-day, then things are really starting to drop out. In this case, 2 days previously, on 16th of September, it was completely cloudy. So the 3-day composite is not adding any new observational data because everything's cloudy, but it is increasing the threshold to call a pixel water. And the other, key thing when you're looking actually at the imagery on a map, or the data product on a map, is, are we detecting the lakes and the oceans nearby? And if, that also gives you a proxy for cloud cover. There's also a insufficient data layer, which you can click on, which is another proxy for how cloudy it is, although it's not perfect, I should say. All right, so that's the basic approach, how we get there. Now I'm going to move on to talking about some recent updates to the product that rolled out in the last year or two. One of the big ones was last year, we updated our permanent reference water data set. The product had used the original Mod 44W, the land water mask product, which was delivered, I think, in 2009. And that was getting increasingly out of date mostly as reservoirs are built, and tropical rivers change course, permanent water changes. And so we were constantly reporting many such areas as flood when they really weren't. So now, since 2009, they had begun releasing yearly Mod 44W data sets. So last year we adopted and are updating our reference water data set, which is based on Mod 44W, it's yearly as well. So the result, as you can see on the right, on the lower example, the Indira Sagar Reservoir in India had been reported as flood in our product, even though it's been around for at least a decade, if not 15 years or something. But now we're reporting it as water, which we showed it is not flooding. It did flood the area at one point, but it's going to stay underwater. The upper example in Basra area of Iraq and Iran border, also we were constantly reporting a lot of flood, and that area is certainly very complex and interesting what has gone on there. But now we're reporting much less flood there. So just a couple examples of that. So that's been in the product since April of 2024. The other update, which is a new feature, not quite out the door, but it's on the threshold, is recurring flood. So this will help us separate out regular flooding or recurring flooding from what is more truly unusual flooding, or at least that is the goal. On the example below, this is again the 2011 event in Cambodia. With our normal product, as you saw in the map earlier, everything was reported as flood, and it was quite extensive. And this was an unusual year, but a lot of that area does flood regularly, as you see in pink in the center panel in October. So if that event were to happen now, it would be delivered, as you see in the lower right, with a lot of it being reported as recurring flood in yellow. But some of it was definitely unusual, and that will be continued to be reported as flood. Here's an example of that in Northern California. This is, not what we were doing in January 2023, but if we were, this is how it would look. So there's often flooding in Northern California, in the northern part of the Central Valley in the winter, and we report it as flood. It is not standing water that's there all the time, but it is there frequently in the winter. So when this happens again this January, hopefully the map will look more like something on the right, where it's mostly reported as recurring flood and not as flood. Here's another example along the Mississippi. Flooding from screwed up on the date. I'm not saying this was April 2025. This was the same example as we saw earlier, right? So much of that flooding was unusual, as you see on the right. Some of it was typical annual springtime flooding, but it was an unusual event, as makes more clear. In recently this month in the Indus Punjab River system in northern Pakistan, there's been a lot of flooding as well. And that, when I first looked at this, I thought, oh, well, this will also be recurring flood, but it's not. It is actually unusual flooding that we've not typically detected in the past. This is actually a sort of manual composite product I made out of 7 days just to get more observations because it was a bit cloudy over that time period. All right, so those were the updates. Now I'm briefly going to go over the evaluation or validation that we did. This was done on the original product, so it was done about 10 years ago. And the purpose was really to, see if the water detection algorithm was working correctly, or where were there possibly big problems, or certain floods or surface water areas problematic. We didn't have any rigorous ground truth data sets. Obviously, this is difficult to collect for a global flood product where typically you don't have much warning that a flood is coming. So we were just doing a fairly simple qualitative assessment using MODIS and coincident Landsat imagery to evaluate how things were working. So we selected 50 events from the Dartmouth Flood Observatory's master list of flood events, 50 flood events, and picked also 50 separate permanent water areas to evaluate for non-flood conditions and water detection. Here's the summary of the results. The flood detection was 66% of the time was good or better, 34% fair or poor. About a third of the time it was simply too cloudy, so we didn't exclude those off the bat. We kind of went in blind, not knowing the cloud cover. Permanent water does much better, about 85% good or better, only 16% fair or poor. The difference is largely because some of the flood sites were, small scale flooding that 250 meter pixel is problematic at. So anyway, it worked fairly well. Here were some examples. Here's Bosnia and Herzegovina flooding in 2014. This is how we use the Landsat pre and post. You can clearly see flooding. Our product on the right, it seems to be picking it up fairly well. So this was, a good performance. Kentucky in 2014, this area floods, fairly routinely. And just looking at the MODIS, you could see that it was dark and water, and effective at detecting that. Here was an area where things didn't work out so well. Volcanic dark soils are problematic because they are quite dark and they often get detected as water, or they can get detected as water in certain places. Mauna Loa was one such place. So we were routinely reporting flood on the top of a pyramidal volcano, which was super unlikely. And this was though solved with the hand mask, which would obviously say that there's no flood water. Flood water is not going to accumulate on top of a mountain like that. But that can still be a problem in other areas. And there are some places where it is problematic, where it's not, where topography doesn't exclude possible water accumulation. Okay, so a brief recap of the limitations. I've mentioned these in passing or perhaps not, but cloudiness obviously is the biggest limitation. If it's too cloudy, that's a false negative. We're not seeing it because it's blocked. False positives from cloud shadows on the edges of clouds also can be a problem. The image on the right shows a little bit of both. I mean, there's also real flooding there, mostly on the left, but in those little bands on the cloud, there's almost certainly some false positives falling in there in the really dark sections. But a lot of the image is completely blocked, so we can't see what's going on. The 250 meter resolution does limit what we can see, particularly in flash flood type conditions or river canyon flooding that's not really that broad, but often is very destructive, like what happened in North Carolina. Water moving, water constrained to a canyon is going to move much faster and be much more destructive. But unfortunately, we're typically not going to be able to observe those. The twice daily observations is definitely helpful, but it's not continuous. So a flash flood that moves through, at 5 p.m., we don't have observations then. We're not going to be seeing it, and it will probably be gone by the next day, a flash flood. Land cover, water under tree cover is not going to be detected because we're being blocked by the trees. Urban areas, as I mentioned, there's too many non-wet objects still around typically. And recent changes in normal surface water extent. But as you saw with the reservoir example, but with that and with the recurring flood, you can easily reclassify our product if you have a better reference water or seasonal flooding layer that you like for your area. It would be a fairly trivial GIS operation to reclassify what is in this product for your purposes. Okay, so I want to move on to distribution, data access. So as I mentioned, the data is generated and distributed in 10 by 10 degree tiles. So there's 287 of those globally over most of the global land surface. The main product is an HDF file, which has all of the flood composites, flood layers. It also has a bunch of ancillary layers with water counts, valid counts, total counts. So you could actually create a different composite or use different parameters to do that if you wanted to investigate more. Along with the HDF, there are geotiffs for just the flood layers, which is probably what most people are interested in. And much easier to work with than an HDF for most folks. And just the table on bottom, it's a data layer. It is not an imagery product, but it's very simple with a few pixel values for the different classes we're reporting. So how do you get these? There are two download sites, the NRT sites, or the Lance download sites. NRT3 is the primary one. There's a backup NRT4. Again, these are duplicate processing and delivery systems. So if one is down, the other one should be still operational, and you can look for the data there. You do need a free Earth data account. That's fairly easy to get. And you need to know the product short names, which is MCDWD for Modus product and BCDWD for the VIIRS. I might walk through this in the demo section, but otherwise you can refer to the slide or the user guide for how to navigate. It's not too complicated, but it's maybe not super intuitive. And these NRT sites deliver hundreds of different data products. So ours is just one amongst many. They only retain data for 1 week. So this is a near real-time product. It is not, unlike most near real-time products, or most near real-time products are based on a science product that is archived and retained forever. This was not developed from a science product, but it was developed initially as an applications product. So that archiving process has not been in place. We have been stashing them away nevertheless, but that will be solved hopefully soon, and there will be an archive available shortly. So aside from downloading the files, which you can certainly do, you can access via various APIs. NASA Gibbs would be the primary one, the Global Imagery Browse Service. This has WMS and related type services with the flood product and 1,000 other satellite imagery products. So it's all kinds of stuff. You can pull that into ArcGIS, QGIS, Google Earth, and that is what's displayed in the NASA Worldview application, which you see on the right. And that's also what is pulled into our custom flood viewer, which you'll see in a minute. NASA Worldview is sort of the main interface to Gibbs for visual browsing. It contains the flood product since early 2021, and the VIIRS, the Modus flood product since 2021 and the VIIRS product since June of this year. What's really nice is you can easily compare to the source imagery, so you don't have to go grab MODIS reflectance imagery. It's in there. You can just easily compare and flip things on and off. It does not host the 1 day product, just our 2 and the 3 day. Because of the false positives in the 1 day, we did not want to make that quite as accessible because people might misinterpret the product when it might be problematic. So that is not in Worldview, but that is in the flood viewer. Yeah, and when you go to the Worldview interface, the first thing that comes up is this Welcome to Worldview. And within that, there are a bunch of tutorials for different types of data products they have. And one is assessing floodwaters. So if you're unfamiliar with either Worldview or with a flood product, you could start there and get a walkthrough. Otherwise, clicking on the Add Layers button will bring up the menu to add any of those 1,000+ layers that are available, including the flood product. The base layers are always displayed. Those are there by default, and these are the imagery layers, and this is what you want to compare against to see if it was cloudy or not, or the cloud conditions for a flood product. Also in Worldview, there's there's an events tab, and a new addition to the events tab are flood events. So if you filter on flood events there, it will list recent events reported by GDAX. And if you click on any of those, it will zoom to that event and bring up relevant layers. Many of those events in GDAX are not major floods, so they may not show up. You may not actually see flooding on the ground. But if you've heard of something in the news, hopefully it will be listed there, and it can bring you to that, and you can see what we have. Okay. Now I'm going to try to show you a live demo with Worldview.
At the Worldview tab. There you go.
So yeah, I'm going to go through this quickly because you had mentioned it in your intro, and I forgot I had talked about this. So if you go to the near real-time data download sites, NRT3, and you could just change this to a 4 and you get to the other one. You click through all data. 6.1 is the secret code for MODIS products. 5200 is for the VIIRS products. This is on that slide. It's in the user guide. And then in here, you have to search for that short name. So these are the GeoTIFF products, and this is the HDF product. You click through here, you see the dates. These are day of years, so you might need a day of year calendar to convert a normal date to a day of year. And here's all the products. So you can download, gives you the size. So there should be 287 of these for all of the tiles. So that's the download system. You can also, if you're looking at different dates, you can just edit this up here and see what's switch to a different day directly in the URL bar. Okay, so that's downloading data. Here's Worldview. This is what it looks like when you start Worldview. The assessing floodwater story is here, but I'm not going to go through that. I just X that out. We'll directly add a layer. Go to the floods category. There's the Terra and Aqua MODIS floods. Let's just look at those. And maybe the NOAA. I'll just add the 2 day products so it doesn't get too confusing. But there's also these are the Opera products, Opera surface water, based on Sentinel and HLS, Harmonized Landsat Sentinel. So it starts you at today. I know there's flooding in Pakistan today, so we can zoom over there. And when you start, there's a lot of, I'm going to turn one of these off, and there's a lot of this gray, which is insufficient data, which is useful. This is more or less telling you when we have too many clouds over the composite period to probably detect water, but not definitively. But it's kind of obscuring. So I'm going to turn that off just for visual clarity. You can turn on labels and coastlines and borders to make sure you know where you are. So here we see the Modus flood product. And this is the VIIRS again. Switch that off. So there's flooding along the Indus again. Now, one of the really nice features of this is, that's Terra. Here's Aqua. Here's NOAA 20. And NOAA, because it's today, NOAA 21. Oh, there it is in. Okay. So you can, for either the NOAA, the VIIRS product or the Modus product, you can look at all of the source imagery and see, where it was too cloudy to see anything or where you might have problems with cloud shadows. The really nice feature is the comparison tool. So we can start comparison. This opens a new tab up here. What we had originally is on the left. We can change what we have on the right. Now it's the same, but let's do something more interesting and go back to 2022. And turn on the Modus. And right, so this was the major flooding in 2022. And as you see, today we have flooding along there, but really in the main track of the Indus. But today we have more flooding in this upstream area that didn't happen, or at least not at this particular date in 2022. So you can quite conveniently compare events or compare dates. You could also have the same date in different products and just swipe between different products. So you really have a lot of things you can do here. You can use the spy tool to do it that way. So there's a lot of capability there, but I don't want to get lost in this too much. So we're going to move on back to the presentation. Let's see. So this is the customized flood viewer focused on flood products. And we also bring in the one-day flood product from both our Modus and our VIIRS, so you can look at that in detail. You can also click on the imagery layers, so you can do all that stuff. It doesn't have a compare function, which we're hoping to bring to it. And we're hoping to also bring in other flood products, maybe the Copernicus Sentinel-1 glow-fast flood product, and hopefully bring in the flood event viewer as well.
So we're not seeing anything on your screen. There we go.
It keeps kicking me out for some reason.
Okay.
Okay, here's a manual, not live demo of the flood viewer. So on the left, we have our VIIRS flood product for flooding in India from a month ago. And on the right is the NOAA GMU product for the same event on the same date. So if this was live, you could click on and back and forth between these two and compare them in detail. I would just say that the NOAA GMU product reports water percent, so it's not a binary product like ours is. So a lot of those yellow areas, as you see, are 50-ish% water, in which we're not picking them up. So it's a very different product, but certainly worth a look. And this makes it easier to do that and to compare them. All right, in the interest of time, I'm going to skip this, but you basically saw it. The product archive. So as I mentioned, we've reprocessed the archive back to Aqua launch. So we have 22 full years from 2003 to 2024. We're finalizing, validating to make sure all that reprocessing worked properly, and adding in the recurring flood class, as mentioned earlier, so it has all of that updated. We're hoping to get that out the door soon, certainly this fall. Moving forward, both the Modus and VIIRS products will be added to the archive, so there will not be a gap there or an issue with getting older products. The archive lets you do lots of interesting things with historical data. It allowed us to build the recurring flood mask, for example. You can also look at trends over time, etc. This is showing a Bangladesh flood event from June of this year on the top. And on the bottom is just the stacked up water observations over 11-year period from 2011 to 2022. So as you can see, there's areas that flood quite a lot, and most of the flooding that you're seeing on the top is probably falling in those areas. If the top image was a recurring flood, had the recurring flood integrated, that would also be quite useful, because probably a lot of that red is flooding that's recurring in the same areas. Here's another historical example looking at Lake Chad, a nice dry area where you don't have a lot of clouds to worry about. And this is looking at 13 years of product, showing how frequently parts of it have water and how infrequently other parts have water. Same for the upper Indus, Punjab river systems. And this sort of supports what we saw earlier when our flood product, with the recurring flood, most of the current flooding September 2025 in this area is unusual, somewhat unusual anyway. And this is also true going back to this period from 2003 to 2015. Whereas on the main stem of the Indus at the far left, there's much more frequent water. Future directions. So all the things I've mentioned, getting the flood viewer. So the flood viewer is available. You'll see the link on the last slide. We haven't officially announced it, or there were some final tweaks and updates we're trying to get done. But you can certainly access it, and let us know if you have any problems. The recurring flood class update is coming hopefully in the next month or so, along with the release of the archive, and archiving moving forward. So that's all like on track and hopefully out soon. The more interesting thing we're working on in the future is a machine learning update to the water detection algorithm for VIIRS. This has been done by a group at the University of Arizona, who are funded by NASA grant. And it shows a lot of promise for not detecting shadows as water, which would be really useful to reduce the complexity of the product from all the you would probably still have the composites, but it'll be a lot more straightforward for end users. It also detects water, seems to detect water quite well. So we're hoping to introduce that into the product in the next several months. Farther off into the future, we would very much like to get the MODIS Flood Archive available in Worldview, so you can click back in time, back to at least 2003, and look at flood events. That's just a kind of compute issue, which hopefully can get pushed through at some point. Further out, there's a Sentinel-3. Sentinel-3 is a European sensor that's sort of MODIS-like, similar resolution. It's different, rather different than either MODIS or VIIRS, but it would provide a morning look, which would be really useful for us because there are less clouds in the morning than there are in the afternoon. So we would very much like to adapt the flood product to use Sentinel-3 when that is feasible to do so. And that's it. That's everything I have. There's a bunch of links on this page to the product homepage, which you can find the user guide, which is fairly extensive. There's a mailing list if you want to hear about updates for any of these things that I said are coming or hopefully are coming in the further future. And links to the Alliance download sites, etc. The flood viewer, although it's not officially been announced, you are free to peruse it at this link, and let us know if you have any questions. You can email me directly, or data-support@nasa.gov will get to the team. So thank you very much for your time. And if you have any questions now, I guess I'll let Jennifer
Perfect.
round that up.
Great. Thank you so much, Dan. All right. Well, thanks, everybody. Just a moment ago, I opened up our final optional polls, and I'll keep those running in the background for 30 minutes or so. So if you would like to provide some input, you have some time. So let's go ahead and jump in here. I want to make sure that I capture some questions or comments that were noted in the chat, but not in the Q&A. And so the first comment that was made was in the chat, and it's let's see here.
I have to scroll down for a moment. Give me a second.
There was a question about whether or not how well does this detect glacier lakes?
I haven't. I'm trying to think if I've ever looked in particular. It should detect them well if they're not in shadow, and then might detect them as a false positive. But I guess the risk would be if a glacier lake, if it's of reasonable size, I think it should detect it fairly well. If it's quite small or if the topographic masks interfere, but they really shouldn't interfere with any permanent water body, because we burn in the permanent water body data set into the hand mask to make sure it's not masking on any known water bodies. But
all right. Well, thank you. Thank you so much. So the first question in the Q&A, and this might be a question that we need to follow up offline as well, but I wondered if either the Q&A panelists or Dan, if you have any ideas for this participant, would you please recommend a research gap that can be a PhD project in African water resources domain using this amazing NASA product? Then the individuals provided some contact information. If you have any thoughts on that, or certainly we could follow up offline with this participant. If anything comes to mind, I thought I would bring it up really quickly here.
yeah, I'd have to think about that more. I think in tropical Africa, the product is, the Congo Basin, tropical Africa, it's probably problematic because of the high cloud cover, very high cloud cover, and high tree cover. Probably in eastern tropical Africa, where you have plains and not quite so many trees, it might work reasonably well. But and West Africa, I'm not sure it would.
Sure. Well, thank you. And I think this is something we can also explore and perhaps provide some more input offline with this webinar participant. So thank you so much, Dan, and thanks to the participant. The next question is, it seems that multi-look compositing step could be a shortcoming or challenge flash flood detection. I am curious if there are ways around it to detect flash floods.
Well, the way around it is to use the 1-day product, because that, although it's the two observations from that day, so there's still technically multi-look compositing, but the threshold is always one, at least one. Well, so any detected water gets into the 1-day product. So yeah, I would, if there's a flash flood or anything time critical, look at the 1-day product, but just be sure to look at the cloud cover, look at the imagery to make sure that what you're seeing is potentially real flood, or if you're not seeing it because it's totally blanked out by clouds.
Okay, thank you very much. The next question is, HAMD is used when flood detection application in basin kinds of regions. What about urban flooding? Does this condition needed otherwise? Okay. Does this condition needed otherwise? There is no flood pixels because of masking.
So I'm not sure I quite understand, but the problem in urban areas is the buildings. We're not masking urban areas out. If there is flooding in a large central square or park that is not tree covered, that will get reported, but it might just be a few pixels, so it might be harder to notice. Or if it's an urban area that has wide streets and they're covered with water, you may well get some flood detections there too.
Okay, well, thank you very much, Dan. The next question I did provide a response to, but maybe if any of the Q&A panelists or you have additional input, how can a student access the NASA products? This is my first time. I potentially use it as an independent researcher, and this is a question from a 12th grader, which is amazing. So my initial response that a good way to get started would be to take a look at the products using NASA Worldview, and that there is a flooding tour story on the main page for that mapping and visualization application, but maybe you have additional thoughts that you'd like to add to it.
Yeah, I would start with Worldview and then the product. I mean, if you want to download the product to analyze locally, yeah, I mean, you can do a lot with Worldview, so I might stick with that, including comparisons. It really, I guess, depends on what type of analysis you want to do.
Sure. And I'm also happy to provide links to some tutorials for using Lance, other resources as well. And so the next question is there a future for the capability beyond the Modis Terra Aqua lifetimes? And I did mention that, of course, there are also VIIRS products from NOAA 20 and NOAA 21, but perhaps you may have more to add here.
Yeah, that's what the VIIRS product is for. Just mentioned. So Modis will be going away sooner or later. It's certainly not going to be around too much longer. The orbits have slipped so far, and there's no fuel to change them. So it's definitely on its last legs. So the VIIRS product is really the way forward at the moment, and then potentially a Sentinel-3 if we are able to bring that in.
All right. Well, perfect. Thank you so much. And then there was also a point mentioned in the chat. Currently, I was just going through the Q&A, and the comment is the hands mask might be able to help Sentinel harmonized Landsat products. I ran into issues in the mountains where the water mask was applied incorrectly, and the blue band was actually negative due to atmospheric correction. This messed up our band ratios for wildfire mapping.
So yeah, potential. I mean, I guess I'm not quite clear on the application, but you could certainly do a variant of the hand mask for a different product. It's very dependent upon the resolution, and your purposes. So if you're trying to apply it to a Landsat type product, you would probably want to rebuild the hand mask, which can be a bit of a chore, but at a different resolution and different parameters.
Okay, thank you, Dan. All right, let's see whether or not there's a couple of other questions in the chat, and then I'm going to hop back down to the Q&A. And I would just ask if you could add your questions into the Q&A panel, that would be great. And you should see that either by clicking on the three dots at the bottom of your screen to pull up your panel options. And insert a check mark next to that, or you might see it as a tiny, almost kind of looks like it's a floating like question mark icon. And then if you hover over that, you should be able to activate the Q&A. So hopefully that's a helpful tip. So let me get to the next question here. All right. Are there any thoughts about making recurring flood masks for various flood returns? I'm not sure what is intended here. If this is meant to say 12 years, 15 years, 1 to 100 years.
I mean, you certainly could based on the archive. What we did was to have something static. So our parameter was if flooding is observed in 7 of the 22 years for that archive within a month, more or less. There's some additional details, but then we'll call it recurring flood. So if flooding is happening there, a third of the years that we've observed things for this data product, we call it recurring flood. But yeah, you could. I mean, this is why a longer data record is better. And unfortunately, Modis only was launched, the first one, in 1999. But that's a good 25 years we have, at least.
Well, that's right. So thank you so much, Dan. The next question is, again, from the chat that I'm hopping back down to the Q&A. What is the lag time for the VIIRS product?
It's still, so the Lance standard, the advertised latency is 3 hours from satellite overpass. The product should be out the door. It is typically, I believe, less than that. The precise time, the orbits are not fixed, so it's unlike Landsat. It's not on a sort of the same sort of fixed track. So if you're familiar with other products, although it's technically, same time of day, the track might be a little bit east or west. So the real time you're going to get it is a little bit harder to know precisely.
All right. Well, thank you, Dan. The next question is, since you're using VIIRS, does its acquisition frequency reliably capture short-lived, flash flood events and the peak stage of floods? If not, how do you handle those gaps? Do you integrate SAR-derived flood extents to augment or validate your Modus VIIRS flood? Oh, okay. Let's do that as a separate question. It's part of the same. Let's see, again, since you're using VIIRS, does its acquisition frequency reliably capture short-lived flash flood events and the peak stage of floods? If not, how do you handle those gaps? And then I'll move on to the second.
Yeah, it's unlikely to capture flash flood events unless they happen to coincide with a morning, with an afternoon, for VIIRS, with an afternoon observation. So depending on the type of flash flood event, it's not going to be ideal. I think it would be unusual for us to capture flash flooding. Maybe you'll capture some aftermath where there's some ponds or pools sitting around for a day or two, but it's really should be thought more of as a kind of a broad first cut look at flooding, and then if you see something, or if there's flooding from flash flooding, you could certainly look here. But other resources, higher resolution resources, would really be needed. And the timing is also very problematic with a flash flood. The water is probably not there very long, so it's a tricky problem, that's for sure.
Right, and there was actually a question posed as to whether or not the product picked up the recent flooding in Texas.
No, it did not. I think for two reasons. The flooding happened in the middle of the night. I suspect, problem two was it was cloud covered for like 3 days completely, like blanket cloud cover after that event. I suspect even if it had been clear the next morning, I think the flood came through in the middle of the night and there was probably not a lot of water sitting around at 10 in the morning when we might have had an observation. So, or certainly by the afternoon. So, again, there might have been pools along the river that were unusual and maybe picked up, but those types of events, unfortunately, that are so destructive are also very, very difficult to capture.
Well, thank you so much, Dan. And the next question is, do you integrate SAR-derived flood extents to augment or validate your Modus VIIRS flood detections? If not, what technical or operational barriers prevent this?
So if you mean in terms of a combined flood product, no, we don't. That is, interesting idea. The flood viewer is sort of trying to provide a way to look at those separate products independently. And I didn't talk about it much, or maybe I mentioned it, but there's the NASA Aqua water products. One is based on Sentinel-1 SAR. One is based on HLS, Harmonized Landsat Sentinel-2 optical data. They're both available in the flood viewer and in Worldview. And so they provide much higher resolution water detection, but they're not available daily because there's not daily observations from any of those sensors. But you should certainly look at those and for any given flood. And if you're lucky and there's data, it may well show you much more accurate water delineation at higher resolution.
Okay, thank you, Dan. I am trying to go in the order of the questions as they were received by their timestamp in the Q&A. We may not get to everything, and in which case Dan, you can follow up with these participants offline. The next question is, would you characterize the product as a, quote, alarm product? For example, here's a flood you may not know about, or is it better used to exploit for post-event consequence and recovery activity?
Good question. Not sure if there's a universal answer. We would very much like to develop sort of an alarm product. The main thing holding us back are these cloud shadow false positives, which can be quite problematic. So that's one reason why we're hoping the machine learning implementation for VIIRS will solve that problem or greatly reduce it. That would really allow us to, have a more of an alarm product. And we would like to add that into the flood viewer. The second part is knowing whether or not that flooding is truly unusual. Our recurring flood update that we'll be rolling out momentarily is one cut at that, but it's certainly not going to be perfect. People will probably complain. We had to make a decision about what we call recurring flood. So it's an attempt to kind of clean up the product in terms of differentiating what is possibly unusual flooding from what is probably a normal seasonal type flooding.
Okay, thank you, Dan. Maybe let's try to, and then we'll reach the end of the Q&A, just due to a little bit of a later start with the content. Are there existing works or projects which have tried to improve these predictions or detections using other satellite products or imagery? If yes, how?
Not that I know of. There, the NOAA GMU product is a totally separate flood product based on VIIRS imagery also. So same sensor as we use for the VIIRS product, but a totally different algorithm. Certainly worth a look at that if you're interested. And there are, there's a lot of different flood products out there, or water detection products, I should say. But the conditions are so variable for flooding globally that it is difficult to find the best product. There are, comparisons between methods and algorithms, and, some things work better here, some things work better there, or different sensors. And that's why our approach with the flood viewer is hopefully more so than we do now, but bring in other products so the users can actually look at them and decide, well, this one's getting only a little bit, but this one's actually much better. This is what I actually need to go download to use for my project or assessment.
All right. Well, thank you so much, Dan. And with that, we have come to an end for this afternoon's webinar event. And what I will do at this point is I will leave the virtual meeting space open an additional 10 minutes, but we will log off from the audio component. So Dan or Diane or Jenny, if you'd like to type in a response to any of the remaining questions that we have not responded to, feel free to do so. Otherwise, Dan and our Q&A panelists will follow up with you directly offline. I'd like to thank all of our participants for your very thoughtful input and your excellent questions this afternoon. We really appreciate you. And I'd like to thank our speaker, Dr. Dan Slayback, for his presentation and subject matter expertise, and to the Lance team, Diane Davies and Jenny Houston, for joining us. And then finally, to my last but not least, my backup host, Geraldine Tuart, and Joseph Smith, for your assistance today. So with that, everybody, we are going to log off from the audio component, and we hope to see you at an upcoming webinar. If you have any thoughts, feel free to enter those into the chat or the Q&A, and I will be sending those logs to our speaker. All right. Thanks so much, everybody. Have a wonderful rest of your morning, afternoon, or evening. Take care now. All right. Goodbye.
Thank you, Jennifer.
You're welcome.